Okay, one of the nice things you can do with DFS is detect cycles, but in fact, this immediately leads to topological sorting algorithm, which is kind of nice. So for undirected graph, the problem is very simple. I give you an undirected graph. I ask you if there is a cycle. Well, you do DFS or BFS or whatever FS. And what happens if there is a cycle, you would detect a back edge. You would detect an edge that does not belong to the DFS. That immediately would imply that there is a cycle. Extracting the cycle itself requires a bit of work, but it's easily doable. So the undirected case is easy. You just do some graph exploration, BFS, DFS, or whatever, and you're done. The directed case is much harder, right? To decide whether or not there is a cycle and detect it. But it's already a question that we implicitly already addressed. Given a graph G, really asking if it has a cycle, if it's directed, just asking whether it's a DAG or not. And if it's a DAG, we know that we can compute a topological ordering of it in linear time, right? So we can just run the topological ordering algorithm that we already have. And this topological ordering, if it fails, right, if there is one edge that is numbered incorrectly, right, it points from a large number into a smaller number, then we know that there is a cycle. Extracting the cycle here requires a bit more work, but also it's doable. But let's not go into how to do that, because we are going to see a much cleaner and nicer way of doing it with DFS. Okay? So here's the idea. We are going to compute DFS of the graph. And if there is a back edge, right, we have a graph, we do a DFS. In a directed graph, we found the back edge. Back edges always go from a vertex in a directed graph to its ancestor in the DFS tree. So we immediately got a cycle. And extracting the cycle is easy, right? Because you just have to climb, if this is edge UV, you just have to climb back along the path to your ancestor V and you have the cycle. So that's good. And the claim is essentially that this would detect a cycle if there is a cycle in the graph. But to see that we are going to do it somewhat indirectly, instead what we are going to do in the end of this DFS, we are going to output the vertices in decreasing post-numbering order, right? Now, this is very easy to do. So DFS naturally would output the vertices in increasing post-numbering order, right? It just, whenever it's set a post-numbering, it increases the timer counter. So we can easily just store the vertices in this order. And in the end, we can just take this output array and just flip it and output it in this order. So DFS can do that. And we claim that this reverse post-ordering, namely decreasing post-ordering of vertices, is a topological ordering of the graph. And the running time is of course linear because we're just doing DFS, so it cannot be better than that. But correctness is completely not obvious now. So we will need to prove two claims to see why this is correct. And the first claim is that if there is a cycle in the graph, then there is a back edge. This is really what we need for the cycle detection. So one direction is easy. If there is a back edge UV, then there is immediately, as I just argued, there is an edge UV, right? That is a back edge. Then there is immediately a cycle, right? Because a back edge implies that there is a path from V to U and there is an edge from U to V, so there is a cycle. So that's the easy direction. Now let's do the other direction. Let's assume that there is a cycle in the graph, right? So V1 go to V2, so on to Vk, which goes to V1. And the idea is that once the DFS, so let's assume the cycle is clockwise, right? The basic idea is that when the DFS hits the cycle for the first time, right? Look on the first visited vertex on this cycle. In the recursive exploration for this vertex, it's going to visit all the vertices of the cycle because that's what DFS does. It reaches all the reachable vertices, right? So all of those vertices are going to be explored when we explore this vertex. Here the proof is called VI. In particular, look on the last vertex before the closing of the cycle. This vertex, VI minus 1, I guess, is going to be a descendant of VI, and as such, the edge connecting it. Now let me try to use it a different color because this is a mess. This edge is going to be a back edge. And the DFS will discover it, whether you like it or not. Right? So it would detect the back edge and it found a cycle, so we're done. So this is already enough to prove that DFS is indeed a good cycle detector. If there is a cycle, it would discover it. So that's good. The second claim is the more astounding news from the previous algorithm, this claim that the post numbering, the reverse post numbering is good. So the claim is a bit technical. Let me prove first the claim, and then I will go down into explaining why it implies what we want. So assume we have a graph G, which is a DAG, and we have a vertex V, and we have a vertex U, and the post numbering of V is larger than the post numbering of U. Then the claim is that the edge UV is not in the graph. Okay, so although I wrote it in reverse, this and this are the same thing, right? So assume that post U is smaller than post V. So let me write U here, and we have post V, right? Intuitively, we finished handling U before we finished handling V, right? Now we can look on the two time interval of U and V and how they interact, right? So there are two possibilities, right? Either the time interval of U is contained inside the time interval for V, right? But that means that we started exploring from V, right? So we have V, and we started exploring, V. We started exploring from V, we got to the vertex U, right? So there is a path from V to U because it's reachable from, U is reachable from V. And then if the edge UV was in the graph, that is our assumption, then there would be a cycle. So this is impossible. The other possibility, of course, is that the time interval are disjoint. U and V are disjoint. But then, what do we have? Post of U was, we did exploration of U before we started exploration for V. But if the edge UV was there, when we explored U, at some point we will try to explore V. And then the interval of V would have been containing U, which is also impossible. So this is a contradiction. Both cases are impossible. So we conclude that our assumption that the edge UV is in the graph is false, and as such the claim is correct. Okay, so now let's see why this is what we wanted. So what did we prove? We proved, again, we did a DFS and we output the vertices of the graph in decreasing post number, right? The vertex with the largest post number is the first one, the second is the second one, and so on, right? Okay, so what this proposition says is now that we have those vertices in this order, V1, V2, V3, and so on to Vn, where we know that the post numbering of for all ij, for all I smaller than j, we know that the post number of Vi is larger than the number of post number of Vj, right? And they are strictly smaller because the post numbering are disjoint, by the way we implemented the algorithm. Now, so this is the ordering, right? This is the ordering the algorithm computed. What the claim says is that there cannot be two vertices, right? So post V is larger than post U in our setting means that we are looking on a vertex Vi Vj, where I is smaller than j, right? So if we look on two vertices, I is smaller than j, then there cannot be an edge from u to v, right? There cannot be an edge from vj to vi. Namely, all the edges in this ordering are going from left to right, which means that it's a valid ordering, which is what we wanted. So this really shows that DFS, the post-numbering, the decreasing post-numbering of vertices by DFS, it did give us a topological ordering of the vertices, which I, by the way, find amazing, right? Because it's like, it's a priori completely and totally not obvious why it's true. So this is really a nice property of DFS. Okay, so here is, we got the following result. Given a graph with n vertices and m edges, we can do a DFS on it in linear time, n plus n time, and this computes a numbering of the vertices such that if uv is directed edges in the graph, then the numbering of u is smaller than the numbering of v. So, and all we did was DFS, which is awesome. Okay, let's see an example. So I'm going to quickly do the pre-post numbering of this graph. So 1, we go to D, so it's 2. We go to F, so it's 3. We go to H, which is 4. Then we return, so it's 5, 6, 7. Right, now from here, from A, we are going to go to E. So it's going to be 8, right? From there we're going to G, so it's 9. We're going to come back, so it's 10. From 8 we are going to go, the numbering is 11. Then from there we go back, so we get 12. Right, okay. Now we start with B, which would be 13, and then 14, because all the vertices out of it is visited. And this is going to be 15 and 16. Okay, now let's see the numbering, the ordering, right? C has the largest post number, so it's first. Then it's B, right? Then it's going to be E, right? It's 11. Oh no, it's A first, right? Because oops. CBA, because A is 12. Then it's going to be E, we're at 11. Then it's going to be G, because it's 10, the post numbering. Then it's going to be D, right? D, and then it's going to be F. Then it's going to be H, right? So let's verify that this is indeed correct, right? Okay, so CBA is definitely a correct ordering because they're all sources. Now EGD is less clear, right? So EGD, that's also true, right? Because G is we can put G, right? As long as we put G after E, we can put it before D, that's fine. So this is correct. And then F and H, right? F have to be before H. So this is the ordering we get, and indeed it's a valid ordering. So this magic of post-numbering of DFS really works. This is it.